Hey friends, so I mechanistically interpreted this neural net, and so I'm going to explain it. I'm going to interpret it. Because if I remember everything, that's kind of cool. And it's ostensibly in my memory. And then once I record this, I can like close my browser because I haven't been able to close it. Okay, so this is a four-dimensional neural net, and okay, so like this is the function that's computing, right? These are like 16 binary inputs, and it's separating these points, the red rows, as I will refer to them, from the blue rows. And the function was chosen randomly, which is kind of awkward because if you're trying to do like semantic interpretation of a neural net, but you don't even like have a comprehension of what the function. But it's fine actually. That's not as big as. So anyway, we'll just get into it here. A little thing about the visualization, like these like three blocks, and these are the inputs. So like these and these rows are the same, but in this matrix, the rows are sorted according to according to this dendrogram, which is just based on Euclidean distance. So the exact sorting isn't all that significant, but so like it's close. So it's like this is the inputs to the layer, this is the outputs to the layer, and this is the target function, sorted according to the output clustering. Okay, great. So like this is the last layer, and we figured out how it works. So what I mean when I say we figured out how it works, I mean like we can look at like these are the parameters. These are the trained parameters found using standard, I think like PyTorch, Atom, we'll just say gradient descent. And what I'm claiming is that we will be able to look at these parameters and like interpret them like they'll make sense. Whoops, wrong click. So we'll do the this is the last layer. We'll do that first. It's easiest to interpret because there's smaller number of different rows. And it's kind of a thing you kind of have to stare at for a while. But like here's the observation. Like the middle two columns are identical to the output to the target function, except for this one row, right? So kind of like in other words, the previous layer has correctly computed the target function, except for on this one input. Also, it's like, like we're not making claims that this is like, it's quite possible this function, like, it's quite possible that this function is linearly separable. Like, I don't think it is. But, like, if it's linearly separable, you can compute it with a single neuron. And you don't need all these layers. But, so anyway, this neural net is not necessarily the most efficient neural net. So anyway, okay, so we got like the middle two columns. They're correctly computing the function, except for this one row. So how do we correct for that? Well, it's like if you put as weights, two large magnitude negative weights, keeping in mind blue is negative. If you put two large magnitude negative weights on the outside columns, on this one row, that would evaluate to blue it would evaluate to red if the weights are large enough magnitude. And on every other row, those weights would cancel, right? Because you'd have like blue, red, which would be like positive, negative. So like in the weighted sum, it would go to 0. Like these 3 rows, we're just gonna say it would also, because that doesn't perfectly cancel, but like these are close to 0, so yeah, so it's slightly different, but it's the same idea. So then, if you have that mechanism on the 2 outer columns, then you just have to set the 2 middle columns. You also want to negate them. You don't actually need 2 of them. You can just negate like one of these columns, and then just have the sum of the 2 outer columns be larger than that weight. And then that would like successfully compute the target function. It would like error correct this one row. And that's what the weights are. That's what they're doing, right? You have like large magnitude weights on the outer columns, and then smaller magnitude weights on the 2 middle columns. And that computes the function. Okay, so let's go back a layer. Yeah, let's see if I can remember. Oh yeah, I remember this. I remember this layer. Yeah. So again, like these rows and these rows are the same rows, right? This is the output of layer 3, which is the input to layer 4. They're just sorted differently. So again, what we need is for layer 3 to take its inputs and produce, like the error correction on this one input, and also produce on the inner 2 columns like equivalence to the target function. And yeah, so right, I think it's basically the big observation here is that all of the output columns like are very similar to this input column. In fact, this output column is like mostly identical to this input column, except for like these kind of like rows here, which I don't actually understand why those are like being pushed down to 0, but they just are. And right, okay, so then let's look at the so anyway, so like the weight array for this column is just going to have like a big red magnitude on that row, because it's basically just passing through this column, and that is like what it has. Okay, so let's look at the 2 middle columns. The 2 middle columns again are like very similar to the negation of this column. Like if we negate this column, which is an input column, we get you get blues, then you get reds, and then you get blues. So these two middle columns are kind of like effectively doing error correction on the bottom two rows. And, right, so, yeah, so they're basically doing error correction on the bottom two rows. So like in other words, they're trying to flip these two rows, yeah, relative to this column. And the thing that distinguishes these three rows is this blue-red pattern in the middle two columns for the inputs. So so for the middle two columns, you're going to have like a blue weight on this fourth column, and then you're going to have like this error correction thing where you where you have like a blue-red here, and you're going to need that blue-red to be large enough in magnitude that it overrides the weight on this column. So then, like, effectively, like in all of these rows, the blue-red will cancel, and this column will pass through, like the negation of that column. And on these three rows, the blue-red will control and will it will force the output to be red. So if we, and also we're ignoring the other column. And yeah, so that's like what you observe. You have like blue, red, like those two columns are basically the same column, so they have the same weight array. And so anyway, like these two blue reds are doing effectively error correction, and then this blue is just passing through the fourth column. Yeah, and then the final column, which is the first column here, it's basically exactly the same thing, except we're flipping, again, we're passing through this fourth column, and so these rows would normally be, if you negate it, it would be red, blue, blue. So you need to, right, you just need to force them to be blue. So instead of having blue, red in the middle, you'll have red, blue. So you have blue, red, and then you're still passing through that third column. So like the big picture, I guess, is that like, like this column, this layer is setting up these rows for the output layer. The output layer is doing error correction on this one row, and otherwise that's passing through like the middle two columns, right? Like these middle two columns are equal to the target function except for this one row. And the way we're producing that setup is basically more error correction. Like we're passing through this column, and then we're using these blue-red features to flip these rows, like so that this so we're, I guess, like we're basically correcting these two rows relative to the target function, and then, yeah, whatever, and then we're marking this one for error correction. Okay, so then there's one more layer, and yeah, there's one more layer. So like this is coming from the raw inputs, like these are the actual inputs. And yeah, we saw that like this last column is being heavily used, and so that last column is here. And yeah, I mean, also if you just look at it, it's like we're, like this one neuron directly from the inputs is correctly computing the target function except for on this row and these two rows. So it's correct on like 13 out of the 16 rows. So it's kind of like, okay, so how do we, what does the weight array kind of look like for this column? Like, can we understand the weight array for that column? You know, like it's, this one column is separating, you know, like 6 points. You know, red, blue, whatever, all of these points. And it turns out you can kind of comprehend what it's doing. Which, yeah. Okay, so let's look at what those weights are. It's like this. Right. Okay, so it's like 2. Yeah, I gotta. Do I already have that typed in though? I thought I typed that in somewhere. Yeah, I thought I'm just gonna type that weight array in real fast. It'll be great. If I can find it. Okay, it's like 1.97 and negative 1.18 and 1.28 and negative 2.2. Yeah. Okay, so we're gonna visualize what that is doing theoretically. Also, I need to get rid of the purple thingy. Yeah. Okay. Alright. Okay. Yeah, so this, you know, this is the 16 inputs. This is if you, you know, display them according to their dot product with the weight array. And, right, I think like the main observation is that if you just look at the, so the thing that's happening is that if you just look at 1, negative 1, 1, negative 1, you know, like the corresponding input has the maximal dot product value. But also like these green, you know, points are in the input set or the accept set. So basically what we're saying is that like 3 out of the 5 points in the accept set are like distance 1 away from, you know, 1, negative 1. And, yeah, and then what the column is doing is saying like, we can also pull this guy. So like if we put a hyperplane like right here, you know, like these 2 red guys would be misclassified and these 2 green guys would be misclassified. So that would be like an error of 4. And basically what it's saying is that like you can pull this green guy up, you know, somehow so that he's now correctly classified. Anyway, so like that's what that column is doing. It's like playing around with the dot product. Right. So I think like for the narrative of like what the neural net is doing is in this one column from the inputs, this one column is giving like a close approximation to the function. It's not actually the closest approximation because, let's see, because this has 3 erroneous rows, and I think I saw somewhere on this you could get it down to like 2. It's possible you could get it down to 0. I don't really know. But anyway, so like for the narrative though, it's like this column is like very close approximation to the actual target function. And then what's happening is that these 2 columns, were like this first column does nothing as far as I can tell, so we're ignoring the first column. But what do these middle 2 columns do? Well, like on every row where this column is incorrect with respect to the target function, it's tagging that row with a blue-red. So it's like blue-red here because this is a blue and it's supposed to be a red. On these 2 rows, they're supposed to be blue, but they are red. And you're also getting a blue-red tag. And, yeah, like that. Yeah, so we can also visualize that on my visualization, which is maybe right here. What are those weights? 0.5, 0.7, negative 1, 0.5, okay. Yeah, so this visualizes that. Or like basically, let's see, I forgot what it was. It was like, it was a weird thing because like if you look at these 2 columns, they're the same function except for the 3 rows that happen to be like erroneous according to the 3rd column. Yeah, so it's trying to, so it's something like in the visualization I had, like you can start with a weight array here for this column or this column, and you can manipulate the weight array such that only these 3 points move across the boundary. And I'm not sure if that requires linear interpretability or not. Yeah, let me see if I can produce that real fast. So we're starting off at, we're starting off at like, okay, yeah, we're starting off at this guy. Negative 0.5, which one is that? Okay, so we're starting off where the erroneous rows are labeled blue. So the purple rows, or yeah, purple inputs here are blue. If we have like, if you imagine a decision boundary over here. And then, but it's saying like you can just move the purple inputs and keep everything else the same to produce, because yeah, like we're effectively tagging these 3 rows as being erroneous. Okay, so anyway, yeah, so I'll try to transition. Yeah, and see what happens to the blue rows. Okay, so we want to go from negative 0.5 to negative 0.8. Yeah, let me do it this way. Okay, so we're at negative 0.5, and then, okay, so bump, bump, bump. That didn't do anything obvious. 0.7 to negative 0.8, so that's like a big movement. Right, so this one is raising the purple guys. Actually, does that solve it? Let me reset. it's kind of hard to eyeball. So the boundary, or like the border, would be like here, making all of these guys purple, or making them all blue. But also these two would be blue, and then you want them to stay blue. So yeah, it's like you're moving the purple guys up. Anyway, that's basically what it does. Right, so the overall narrative is, and this isn't something that like a human, I don't think a human would ever really be able to program this, because kind of the human would have to be like, hey, the accept set is very close to this red blue thingy. And so then, like, if I use that, if I put a hyperplane there in the fourth column, then that produces like 3 erroneous rows. And so then I can use these 2 columns to tag the erroneous rows. And then, like, I don't know, yeah, keep going through the layers. Yeah, so anyway, I can like close my browser now, so that's cool. Yeah, and I'm gonna look at some more 4-dimensional neural nets, and see what they do. So